Hi, David. How's your day been going, Professor?
It's been good. Yeah, I started grading your guys' midterms. And by started, I mean I did one, and then I got pulled away to do something else. Um, so I'm hoping to finish grading those by tonight. So probably sometime later tonight, I'll have those graded.
Okay.
How about you?
Good. I decided to do steaks and eggs before I took an exam.
Sounds good.
Yeah. I pretty much I woke my family up at like around uh because I got up at 5:25, so I think around 6,
Mm-hmm.
or at least that's when I have majority of the stuff done.
I see. Did wake your family up?
Yeah, yeah. So like my class started at like 8:30, and I want to at least try to get like 2 hours of study in. So I decided to wake up at 5:25
Uh huh.
and try to see if I could make breakfast within that time frame. It spilled over to like 6:20, but it was okay.
Mm-hmm.
My sister gave me the death stare when I woke her up, and then she went back to sleep.
Hey, Professor.
Hey, how's it going?
Pretty good.
Oh, Professor, have you had any favorite projects that you were working on?
Favorite projects?
Yeah.
I'm not sure. I haven't really thought about it in that way, I guess. 'Cause like I said, every project's different, and every project is kind of interesting in its own way. Um, yeah, I don't know. I really like all the projects that my graduate students are working on right now. Just because it's kind of been my first role as kind of like an advisor. Because usually, up until I started this job, like I was kind of just working on my own stuff under the mentorship from my own advisor. But now that I'm kind of in the advisor seat and kind of seeing my students kind of explore and kind of work on their projects, that's been really cool. So I'm really enjoying that right now.
Okay.
Okay, so it's 2:30, so let's go ahead and get started today. Good afternoon, everyone. It's our first class meeting after the midterm. So how's everyone doing today?
Doing good.
Good. Good. How was the midterm?
Last problem kicked my ass.
Oh, I see. Yeah, so I've started grading it, and when I say I've started grading, I've graded literally one of those. And so I was hoping to have more graded by this time today, but I got pulled to do something else. So I'm going to continue grading it after the lecture today, and then probably finish it up tonight after dinner. So I wanted to have them finish grading before Wednesday, and so I'm hoping to finish all of them by tonight. And so hopefully by tonight, you'll know what you got on the midterm so far. Or what you got on the midterm. So I don't want to comment on what I've seen so far, just because I've literally graded only one. And so let's talk about that on Wednesday once I have all of those graded. Okay. All right. And so the plan for today is we're going to continue on with our lecture notes about the introduction to convection. And so this is the second half of lecture note 05. And so we should get through most of it today. We might have a little bit we need to finish on Wednesday. And then Wednesday we'll start, a specific topic in convection, which is external convection. Okay. And I have not assigned another homework assignment yet. I'm going to wait until we kind of finish external convection to do that. And so for now, I know there's kind of a big flurry right before the midterm. So there's homework 3, and I'm sure you guys are studying for the midterm too. So I wanted to give you guys a little bit of a break before I assign the next homework assignment. Okay. All right. So are there any questions that I can answer before we get started today? Okay. All right. So if there's no question, let's go ahead and get started. Okay. And this is the continuation of our last lecture that we had last Monday, which was Introduction to Convection. Okay. And so this whole unit on convection is almost, almost a little bit different than, what we've been doing up to this point. Because if anything, it's kind of providing a lot more context to, something that we've been using a lot up to this point. Because, up to this point, we've been using convection. So convection's been present in our problems, but the only way that we've really interacted with it was through, this convection coefficient, right? And so we've had this kind of mysterious parameter h, which up to this point has always been given to you, right? And whenever you're given h, what you can do is you can use it in in problem solving, right? And so let's take kind of a usual situation where maybe we have a radial heat transfer here, right? And we have a fluid flow on the outside, and so we have heat transfer due to convection. And one thing, and we've worked with this h a lot. So like one way that we can work with this, we can just simply say that the heat transfer rate due to convection will be h times a, or where a is the surface area, times T at the surface minus T infinity, right? And so that's one way that we've used h. Another way that we use h is we computed the the convection resistance, right? And so the thermal resistance associated with convection is 1 over HA, right? And so we've been working with convection a lot up until this point. But that's under kind of the big caveat that we know what this is, right? Because we haven't really talked about what this H is and where it really comes from. We've kind of just been given it. We've just been kind of given it to us in the problem. Because in reality, this H is a very complicated thing to measure. Right? Okay. It's very different from the other thermal property that we've been using a lot, which is thermal conductivity, K. And so K it is not, because thermal conductivity, that's a lot easier to measure because you can run experiments on this, and it really only depends on just the the material itself. But H here depends on so much more than just the fluid, right? So because it depends on the not only the thermal properties of the fluid, so things like its density and things like that, but it also depends on the nature of the flow as well. So how fast the fluid's going, the flow patterns, how it interacts with the surface and everything. And so in reality, H is not something we can just look up in a book because H is going to be different for every situation. Okay. And I think where we left off on was this expression. So we kind of, we talked a lot about boundary layers last time and, how, the velocity boundary layer and the thermal boundary layer, how they interact, right? And we ended up with this expression for H, right? It's not a very useful expression, but it will at least tell us, some of the things that H depends on. Okay. And so this is the formula that we got for H, and we did this, based on our boundary layers. And then from this expression of H, this basically tells us that H depends primarily on two things. Okay? And so the first thing that it depends on is Kf. And so, Kf here is the thermal conductivity of the fluid. And so that's one thing it depends on. And so that's basically just, the thermal properties of the fluid itself, right? And so if your fluid is just naturally more, easier to conduct heat, that's going to lead to a bigger H, and that makes sense, right? Okay. And then this other quantity right here, partial T partial Y at Y is equal to 0, what this is the temperature gradient next to the surface. Okay. And this is a thing that's usually difficult to compute, because this is a property of the boundary layers. It's a property of the fluid flow, and computing this is really difficult. And that's why this expression here, most of the times we don't actually use it to compute h. Right? But it at least gives us an idea of what h really depends on here. Which is kind of going to be the starting point for a lot of the theory that we're going to go over the next few weeks. All right, any questions on this so far? This is just kind of a recap of what we did last Monday, because it's been kind of a while since we looked at this stuff. Okay. All right. And so, one other, another idea that I want to give to you guys is that h here, our value of the convection coefficient, it's actually, a local quantity. And so what I mean by that is that, the value of h is not going to be the same all around a surface, right? So let's say that we have kind of a potato looking or ditto shaped surface that looks like this, right? And so if we have fluid that's kind of blowing at this surface right here, right? If we compare the value of h here at location 1 compared to location 2 and maybe to location 3, because the nature of the flow, the nature of the fluid flow looks different at all of these different locations, the h value is going to be different at all 3 locations as well. And that complicates things, right? Because normally when we want to use h in our calculations, we want to just use just one value of h, right? Because then we can just plug it into either a thermal resistance, or we can use it as boundary condition, things like that. Right? And the way that we can do this is we can just simply take all the h's at all the different locations on our surface and just simply take an average of them. Right? Okay. And then typically the way that we do this is we do it by integral, right? And so we're going to make use of the mean value theorem from calculus, right? And so the h bar, and I'm using bar here to denote average, right? Usually the way that we do this is we take, say that we have some two-dimensional surface here. And so if we take kind of a double integral over a surface, and then we integrate that local h, or in other words, we're integrating, all the different values of h at different points on our surface. Okay, we integrate that over a surface, and then we divide by the area. This is essentially how we would get the average h over an entire surface. And so, I will say that, in terms of just hand calculations or analytical methods, which is, what we're doing in this class, this integral is usually, it's too much trouble to do this by hand. And so usually, what's done is that you run, people will typically run like a computational simulation, like either a CFD or a couple, CFD and heat transfer simulation. And then, once they get the results of that simulation, then what they do is that you can compute H kind of locally all around the simulation. And then you can ask the computer to perform this integral for you. Right? And so normally, this kind of integral, if you're doing more than just a single integral for any kind of practical situation, that's usually, not feasible for kind of, a human to do. And so a lot of times, these kinds of calculations are done via computer. But at the very least, you should, I want you guys to kind of make this distinction between, the average H, which is what we have been using, versus, the local H, which is kind of what it is in reality. Okay, any questions on this? All right. And so for this class, we're not going to be doing the full 2D integral, but we are going to be looking at various one-dimensional cases. Okay. And so an example of this that we'll look at a lot, maybe probably starting on Wednesday of next week, is flow over a flat plate. Right. And so, we have a flat plate that looks like this, right? We have flow coming in just like that. Right? And so we have basically just one direction here. So we have just the X direction, right? And we can say that the length of the plate here is L, right? In these one-dimensional cases, we can actually compute the average one because, we're just integrating over one surface, right? And so the average H in these kind of simple one-dimensional cases is just going to be 1 over the length integral from 0 to L of H local of X dx. Okay. And we'll do an example of this, very soon. Okay. And so even though, the general case for like that surface integral that I showed you on the previous page, that's a little bit too complicated to do by hand. But for, a simple one-dimensional case where we're just integrating in one direction, these we can actually do. And I'll show you kind of, an example of this very soon. Okay. And so that's kind of an introduction to H and, not only, what values or what things that H depends on, but also, the fact that H can actually change onto various locations on the surface, right? Now let's introduce, the actual problem of convection heat transfer, which is what we're going to be working on over the next few weeks. And so, this problem of convection heat transfer, it's when you state it, it sounds fairly simple, right? But the actual complexity of actually computing this is really complex, right? And so the idea behind this kind of this problem of convection heat transfer is this. Because once you know H, and so let's say that the convection coefficient for your entire surface, once you know that, then you kind of know everything that you need to know about the convection heat transfer, because then you can use, any of the methods that we went over, in the last unit. So you can either use thermal circuits, you can use heat equation, right? Once H is known, then you're basically good. So you're basically kind of good to go. Okay? The problem is H is seldom ever known well, right? And so, the problem of convection heat transfer is to solve for that H. And so over the next few weeks, we'll be looking at basically lots of different methods that we can use to solve for H. Right? And so in some sense, we're kind of, going to take a little bit of a break from all the things that we've done up to this point, and really just focus on what are ways that we can solve for H. Okay. And just like we talked about before, this problem of solving for H is really complicated because it depends on so many different things. Right? It depends on so many factors. In fact, that over the next couple of weeks, we'll spend 1 week talking about flow over an external plate, and then we'll spend another week talking about internal flow situations like flow in a pipe, right? And so coming up with kind of a general rule and general way to solve for H. Right now, it's impossible. It's kind of too complex for a general approach. But for certain situations that show up pretty commonly in engineering, there are some methods that are out there, and some of them are based on some experimental findings combined together with some analytical approaches as well. Okay, and so when people talk about the problem of convection heat transfer, they explicitly are talking about how do we actually solve for H. Okay. All right. Any questions on this before we jump into a quick example? Okay. All right, and so in this example, let's do a quick computation for how we can actually compute the average convection coefficient, right? All right, and so for in this example, we're going to have flow over a flat plate. Okay. So this situation looks like this. And so we're going to have fluid that's going to be blowing in from this way. Okay. And just like we talked about a week ago, once this fluid, starts contacting the plate, what's going to happen is that a boundary layer is going to form. And so this, line that I drew here, this is the fluid boundary layer. Okay. Where this blue line in particular, this is the boundary layer thickness. But remember, we gave it the symbol delta. Okay. And so let's say in this particular situation, for this for this flow over a plate, some experiments were done, and they were actually able to determine the local convection coefficient. Okay. Okay. And so this local convection coefficient is going to be a function of x because it's going to depend on where you are. It's a function of x, right? And so we'll say that it's h of x is equal to a times x raised to the minus 0.1 power. Okay? Where a at this point is a is just some constant. Okay. And so I will say that this particular situation here, where we know the local convection coefficient, this is pretty rare, and so you would need some fairly sophisticated experimental setups, or some fairly sophisticated computational experiments to do this. Right? But this example here is just to kind of show you how you can take a local quantity like this and use it to compute the average, right? And so in this problem, what we want to find is we want to find an expression for the average convection coefficient on this plate. Okay. All right. Any questions on the on just the setup for the problem? Okay. And so to find the average h, what we're going to do is we're going to use our formula that we had kind of 2 pages prior, right? And so we're going to have h bar to be equal to 1 over L integral from 0 to L of h local of x dx. Right? And then what we're going to do here is we're just going to simply take this expression here and then plug it in for h local and then perform the integration. Okay. Okay. So let's go ahead and do that on the next page. And so we have h bar is equal to, after we plug in for h local here, what we have is a over L integral from 0 to L of x raised to the minus 0.1 power dx. Okay. At this point, what we can do is we can integrate. And so if we perform this integration, what we have is a over L times x raised to the 0.9 divided by 0.9 evaluated from 0 to L. Okay. No question. Oh, back one page. Yes, I can. Okay. Are you good? Okay. Okay. And so if we evaluate this integral from 0 to L, all we get here is just the following. And so we get h bar is equal to 1.11 a L raised to the minus 0.1 power. Okay. Right. And so this is basically, you know, the average h that we can use in calculations. Okay. And so, you know, when you're finding, you know, when you're using kind of the methods that we'll talk about over the next few weeks, and you see that, you know, your h is a function of x, you know, you can't use that h directly into some of our older methods because our older methods assume just one single value for h. And so in order to use our old methods, you have to take an average of h over the entire surface. Okay. All right. Any questions on this?
Is that a 0.1 or 0.9?
Wait, where?
Right after like how you you integrated, this is like 0.9, and then the last one where it says like L to negative 0.1.
Yeah, it's L to the negative 0.1.
Okay.
Yeah. Yeah, the 1.11 comes from basically you do 1 over 0.9. So that's where that one comes from.
Okay.
Right. Okay, so that's you know a case there. So that's the difference between local and average convection coefficients. Now let's talk about some of the flow conditions that's going to affect our calculations here. So in particular, we're going to talk about the difference between laminar and turbulent flow. Okay, and so you know, hopefully these terms are familiar to you from fluids, but if not, it's okay. We're going to go over you know, we're going to go over it again. Okay, so to kind of illustrate that, let me draw a plate here. Okay. And then just like always, we're going to blow some fluid at it, right? So the fluid's going to come in like this. And just like we saw in the previous example, a boundary layer is going to start to form. Okay. But once you reach a certain point, this boundary layer is going to start to go kind of a little bit crazy like that. Okay. And then once the boundary layer starts to go kind of crazy, we kind of separate that from the initial part, right? And so this initial part of the boundary layer here where, our curve is kind of growing nice and smoothly, we call this the laminar region. And where the flow starts to get a little bit crazy, we call this the turbulent region. And so if you actually look at some of the, the actual nature of the flow in these regions, you should see a stark contrast. Right? And so in the laminar region, what you should see is that the flow looks very nice and orderly. And so, we have flow that's going, parallel to each other. It looks very nice and, it's laminar. Okay? And so if you draw some of the streamlines, they look like this. And so you have a bunch of straight lines that, are going like that. And so, whenever you have someone talk about laminar flow, basically what they mean by that is the flow patterns look orderly. Okay. And so if you contrast this with turbulent flow, it's going to look like this. And so instead of being kind of nice and straight like this, the flow patterns start to look really chaotic. Right? Okay, so you're going to have, flow that's kind of, zigging and zagging, maybe recirculating, right? Okay, so it's going to do all these kind of crazy things. Okay? Next to the wall, though, usually the flow is pretty parallel to the wall right there. But, once you get farther away from the wall, the flow starts to get a lot more chaotic. Right? And so when we talk about turbulent flow, what I mean is basically flow with a lot of chaotic random fluctuations. And so I bring this up here because these flow patterns are going to have a dramatic impact on the on the convection heat transfer. Okay. And so, oops. And so it's going to be really important for us, once we start doing these convection problems, is to characterize the flow, right? And so what you'll see is that, if we find that we have laminar flow, that's going to, allow us to use a certain set of, equations and a certain kind of, problem-solving methodologies. Versus if we have turbulent flow, that's going to drive us down kind of a different path with different equations and different methodologies in order to solve the problem. Okay? And so, beyond this, this is kind of all the fluid mechanics that you would really need. So just to kind of summarize, whenever we say laminar flow, what we mean is kind of nice and orderly flow. And by turbulent flow, what I mean is, flow with a lot of chaotic and random fluctuations, right? And whether the flow is orderly and whether the flow is chaotic is going to have a big impact on our convection heat transfer. Okay? One other thing that I want to note here before we turn the page is that if you notice, once I got to the turbulent region, the boundary layer just starts to kind of jump up like this, right? And that's by design. And the reason for that is, whenever you have a turbulent flow, their turbulent boundary layers will grow a lot faster. And just like we talked about at the beginning of lecture today, where we stated that the value of H depends on the nature of the boundary layer, the fact that the turbulent boundary layer grows a lot faster is going to have a big impact on the results as well. Okay. Any questions on this?
So for the turbulent, it has a chance of pushing the heat back to the source.
Well, we'll talk about that more in kind of a bit. So actually, the fact that we have these random fluctuations is actually going to help. Because more than not, actually, more fluids actually can be pushed away from the surface. And that's why you kind of see the boundary layer kind of grow a little bit faster. Because any fluid that goes towards the surface is probably basically just going to bounce up and just come back up. And so you kind of have a net flow upwards. And that actually enhances heat transfer.
Okay, thank you.
Okay. And so now that we've seen the difference between laminar and turbulent boundary layers, we can see that it's going to be really important for us to determine whether a flow is laminar or turbulent. And so the way we do this is we compute a non-dimensional number called the Reynolds number. Okay. And so if you remember from fluids, the Reynolds number is given by this this expression right here. And so we usually give it the symbol Re. It's computed by taking the density of the fluid multiplied by the velocity, and then we multiply it by some length, and then we divide it by the viscosity. If you're given the kinematic viscosity of the fluid, which is just simply dynamic viscosity divided by density, another expression is the following. So we take U times L, and we divide it by mu. Okay. And so let me label all of the terms here. And so first thing we have rho, and this is just simply density. Okay. U infinity right here, this is the free stream velocity. Okay. L is just going to be simply a length. Mu here, this is the dynamic viscosity. And nu here is the kinematic viscosity. Okay. All right. And so computing the Reynolds number is just basically just plugging in for all of these guys. Okay. And the way that we use this to determine whether a flow is laminar or turbulent is we check the value of the Reynolds number against the critical value. Right? And if the Reynolds number is less than the critical value, right, what this tells us is that what we have a laminar flow. Okay. But if the Reynolds number is greater than the critical value, then this tells us we have turbulent flow. Okay. And so that's all it is basically. And so, to determine whether a flow is laminar or turbulent, all you're going to have to do is just compute the Reynolds number, check it against the critical value. And if it's less than that, you're laminar. If it's greater than that, then you're turbulent. Okay. And so, what the critical Reynolds number here is it really depends on the situation, right? And so external flow situations have a certain critical Reynolds number. Internal flow has another critical Reynolds number. And so what you'll see is that, depending on the situation, we're going to have a different value for the critical. The idea is the same. And so you're always going to compare the Reynolds number to this critical one and use that to determine if the flow is laminar or turbulent. Okay. Any questions on this? Okay. And so, now that we've kind of talked about laminar and turbulent flows, let's talk a bit about, how the velocity and temperature vary within the boundary layer. In particular, how these things vary in the presence of laminar flow versus turbulent flow. Okay. Because depending on the nature of the flow, these things are going to look different. So let's start with velocity. And so if you remember from last week, what we have in the boundary layer is that the velocity varies from 0 at the plate up until the free stream velocity. Okay. And so let me draw two situations here. Okay. So on the left, I'll draw the laminar situation and the turbulent one. And so the endpoints are going to be the same. And so for the laminar case, and here, let's see, here is our plate. And so at the plate here, we're going to have 0 velocity. Okay. And that's because of the no slip boundary condition, right? And so for turbulence, we have the same thing. Okay. And so in both cases, we're going to have 0 velocities at the plate. Okay. And then at the top of the boundary layer, our fluid velocity is going to reach U infinity. Okay. And so by the time it reaches the free stream, or if we travel a certain distance away from the plate, the velocity matches the free stream. Okay. And so the endpoints are going to be the same here, but how they vary from the plate up until the free stream is going to be different. And so for a laminar boundary layer, what you have is a very nice gentle variation from the plate condition to the free stream. Okay. And so it almost looks like a parabola, right? And so here we have a nice gentle variation between the plate condition and the free stream. For the turbulent one, it's a little bit more violent. And so what you have in the turbulent boundary layer is that you have a very large change very quickly, right? And then from there, it kind of tapers off just like that. Okay. And so what you have here is a rapid change initially. Then after that rapid change, the change starts to slow down. Okay. Okay. All right. And so even though the endpoints are going to be the same for the laminar and turbulent boundary layer, how they get there is going to be different. And the significant thing for this, if we can kind of relate this to what we talked about at the beginning, if we look at the region that's like right next to the plate, right, then what you should see is that when you have turbulence, this near wall derivative or near wall gradient is much more extreme. Right. Remember, we characterized this near wall gradient with the formula, partial u partial y. Once we have, if we have turbulence, then this du dy here is going to be greater than that. Right? And what that tells us that if that derivative partial u partial y is greater when in turbulence, that's going to give us a higher amount of viscous shear stress. Right? Because remember, viscous shear stress depends on the viscosity of the fluid and also that near wall gradient. Right? And so if you covered, boundary layers in your fluids class, hopefully, one thing that you talked about was that, if you have turbulent flow, then you have a higher viscous friction force. Right? And this is kind of the reason why. And the reason why is because, you have much sharper velocity gradients next to the wall compared to the laminar case. Okay, and so this was the variations of velocity in a laminar versus turbulent boundary layer. And so now we're going to do the same thing for temperature, and then we'll talk about, how that affects the convection heat transfer. All right, any questions on this? Okay. All right, so let's look at temperature. And so just like, the velocity, I'm going to draw, two diagrams here, right? One for laminar flow. And one for turbulent flow. And so we're going to have a plate condition. And the plate condition is going to be the same in both cases. And so in both cases, the plate is going to be at a temperature Ts. Okay. Right, and so we have Ts on both sides. And then just like the velocity boundary layer, at the top of this graph, we're going to have the free stream condition, which is T infinity. Okay. And then we'll say that the free stream temperature we'll assume is less than the surface temperature. Right? And so, just like the velocity case, we have the same endpoints here, but what's going to be different is how they're going to vary, right? And so just like the velocity case, if you have a laminar boundary layer, what you have is a nice steady change in between the two. Okay? Versus if you have a turbulent boundary layer, you're going to have a rapid change at first, and then, it's going to taper off after that. Right? So it's going to look more like this. Okay? And so this is gentle variation. And so when you have turbulence, this is much more violent and much more rapid. Right? Okay. Right. And once again, what you should see is that in the near wall region, the turbulence is going to have, if you have turbulence, that's going to increase your wall gradient, right? And so if we compare the values of dt dy at both cases, right? And so this is for, laminar, and this is for turbulence, right? Right? So we compare the, the derivative of temperature near the wall. What you're going to see is that, dt dy in the turbulent case is going to be much, much higher. Okay? And if you remember, from the beginning of the lecture today, what we saw was that the convection coefficient H depends on this, temperature derivative, right? And so because the convection coefficient depends on this, what you'll see, hence, is that if you compare H laminar compared to H turbulent, what you'll see is that H turbulent is, generally higher than H laminar. Okay. Okay. And so, if you want to enhance, your heat transfer, convection heat transfer from your surface more, it's better to actually have turbulent flow. Because of because a lot of the chaos in the flow actually enhances your heat transfer, kind of like what I mentioned before, right? And so actually it's pretty common where if you have a situation where you want to increase the amount of convection heat transfer, what people will do is that they kind of artificially create turbulence over their structure, right? And so if you have kind of a surface, what they'll do is they might add like a little bit of a tripwire, they call it, or any kind of rough surface to kind of induce the flow to enter turbulence kind of faster than what it would normally. And what that will do is that will it will cause your convection heat loss to be even greater. Okay. All right. Any questions on this? Okay. And so let's just let me just write down kind of physically what's going on, or the physical reason why we get more heat transfer in turbulence. Okay. And it kind of boils down to the flow patterns, right? And so if you remember from the kind of the original diagram that we drew of laminar versus turbulent, turbulence had a lot more chaotic fluid motion. And because we have much more chaotic fluid motion, what this does is that it better, or it enhances the mixing of the fluids within the boundary layer. Okay. And so, what you can kind of think of that is, because we have, this chaotic motion and because we have this mixing, you can almost think of it as like fresh fluid is being brought to the surface, a lot more quickly or a lot more often than in laminar flow. Okay. And so if we kind of draw a case right here, right? And so let's say that, I'll draw our two regions here, right? So we'll have laminar and turbulent. Okay. Right. In the laminar case, what you have is the flow is strictly just going from left to right, okay? And so that's fine. And so, what that's going to do is that it's, once these fluid particles kind of heat up, then they kind of get swept along the flow that way, right? But in the turbulent boundary layer, what you have is not only is there kind of a bulk motion from left to right, because of this chaotic motion, what you have is some fluid from the surface going to come up here, and some fluid from the top of the boundary layer is going to go towards the surface right there, right? And this is kind of constantly happening because of the chaos, right? And so because of that, what tends to happen is that in turbulent flow is that a fluid particle will heat up. Then because of the chaotic motion, it'll be kind of swept up towards the top of the boundary layer and then be replaced with some other fresh fluid that goes down there, right? And so because of you have this kind of circulation and kind of chaos, more fresh fluid is kind of brought to the surface, which helps to enhance heat transfer, right? Because then we kind of maximize that amount of temperature difference, as much as we can. All right. Any questions on this?
As a dumb one, but so like the effect would be like that in a jacuzzi for transferring the heat.
Oh yeah, absolutely. No, I think that's a great analogy right there. So yeah, if you if you're sitting in a jacuzzi and you're kind of just and you leave the jets off, eventually the pool will heat up, right? But if you turn the jets on and the jet is spraying hot water in there, that helps to heat up the jacuzzi a lot faster because you're enhancing much more chaotic, much more turbulent flow in the jacuzzi. Mm-hmm. Right. Okay. And so that's everything I want to say about laminar versus turbulence. And so what you'll see over the next couple of weeks is that we kind of have one set of equations for laminar flow and one for turbulence, and because they're pretty different. And so now let's talk about non-dimensional numbers. Right, specifically for convection. Okay, so hopefully you've seen non-dimensional numbers before. Actually, we've already seen one in this lecture, right? And non-dimensional numbers are common in science because what they do is they often report a ratio. And so what I mean by non-dimensional numbers is that they basically have no dimensions. And so it doesn't have meters, it doesn't have newtons, it doesn't have joules or watts or anything like that. So it's totally just dimensionless. And so they have no units or dimensions, and the reason for that is because they're usually ratios, right? And so a ratio is nothing more than just a division between one certain quantity and another. And oftentimes, just to make sure you're comparing apples and oranges, you're what you have on top and the bottom has the exact same units. And so actually, we've seen one in the previous unit actually, right? So we've worked on, the Biot, we've worked with the Biot number, right? Okay. And so you remember from the Biot number, the way that we compute it is we did HL divided by K, right? And what we said back then was that this Biot number was a ratio between convection heat transfer over conduction heat transfer. And so since we're taking a ratio of two things with the same units, those units end up canceling out and we get something without it, right? But just because, we have no units here doesn't mean that it doesn't express anything. In fact, what we saw was that the Biot number would tell us, whether we can use the lump capacitance method or not, right? Because remember, one of the conditions that we needed to have satisfied for the lump capacitance method was that our object was all the same temperature. And in order for that to happen, conduction heat transfer needs to be a much stronger than convection, right? That's why we had that check to see, if Biot number was less than 0.1. And we've actually already seen another non-dimensional number in this very lecture, right? And that's the Reynolds number. And so the Reynolds number is rho UL divided by mu. And just like the Biot number, this is a ratio, right? And so what it's a ratio of is it's a ratio of, let's see, inertial forces, inertial fluid forces over viscous fluid forces. Okay. And so inertia is the forces that are associated with motion in a fluid, right? And viscous fluid forces are forces that associated with viscous shear stress. Okay. And what tends to happen, in fluids is that as inertia starts to dominate, or as the fluid gets faster and faster and has more momentum, then that usually makes the fluid turn turbulent, right? And so another way to interpret the Reynolds number is that as the inertial forces get higher and higher relative to the viscous forces, that's what makes the fluid turn turbulent. Okay. And so the way that we usually obtain these dimensional numbers, in general, is that they're usually obtained by taking your governing equations and non-dimensionalizing it. Okay. And so, Mike, for the Reynolds number, if you wanted to derive that or get its expression, what you would do is you would take the Navier-Stokes equations and you would just non-dimensionalize everything. Okay. And so what I mean by non-dimensionalize is that you kind of plug in a characteristic, expression for all the variables, right? So you plug in a characteristic length, characteristic velocity, and all that stuff, right? And so, this process of non-dimensionalizing an equation, if you haven't seen it yet, it's probably not surprising because it's, usually this is kind of a graduate thing. So I usually don't do this. I usually only do this with my grad students, especially for grad fluids. And so we're not going to do that here. But, I do want to kind of let you know that, this is kind of where it comes from. And, the two new dimensional numbers that we're going to talk about, you can obtain these by, non-dimensionalizing the heat equation, which is generally our governing equation for heat transfer. Okay. And so the process, through which we obtain these non-dimensional numbers, for this class is not super important. So, I would never ask you to derive, these non-dimensional numbers. But I just want to let you know where they come from because we're going to be working with them a lot over the next few weeks. Okay. All right. Any questions on this? Okay. And so, I'm going to give you basically the expressions for these non-dimensional numbers, and what I want you to kind of think about, or what I want you to keep in mind, is not only just the equations for these, which is obviously very important, but I also want you to think about what do these what kinds of ratios do these non-dimensional numbers represent, right? And so I want you to focus more on kind of what I've boxed in red right here, which is what they represent, because it's one thing to be able to compute a non-dimensional number, but to really kind of use it in practice and to really kind of understand it, you have to really understand kind of what it physically means. Okay, so let's start with the first number that we'll talk about, which is called the Nusselt number. Right. So it sounds like the name of a candy bar or something, but it was the name of a dude. He studied heat transfer a lot, right? And so the Nusselt number will give it the symbol Nu. And the way that we compute it is we take the average convection coefficient, right? And so this is H bar multiplied by L divided by KF. Okay. So let me label these guys. So H bar here, this is the average convection coefficient. Okay. L, simply just a length. And then KF right here. This is the thermal conductivity for the fluid. Okay. All right. And so, probably what you're thinking of, because I just kind of wrote it on this past page, is that, the Nusselt number looks exactly the same as our Biot number, right? And so Nusselt is just HL over K, F, and then Biot is also HL over K, right? And so, you kind of already understand, what Nusselt number is. And so it kind of represents the same thing. So it's a ratio of basically convection heat transfer to conduction heat transfer in a fluid. And so I don't really know the history behind this number. So I don't know if the Biot number came first or the Nusselt number came first, but it kind of looks like one person copied the other one. Okay? Because the Biot number is typically, we use that for solids, and the Nusselt number, we usually do this for fluids, right? And so I don't know which one came first, but if this is kind of the rules that science is playing, then I can define this exact same number, but I can do it for orange soda. And so I can say that can be the Justin number, which is the convection coefficient times the diameter of the soda can divided by the thermal conductivity of orange soda, and we can call that the Justin number. But I don't write the rules; I just teach it. So maybe that's not allowed. But Nusselt number is very similar to Biot number, and so that's why I kind of introduce it first, because they have kind of similar things. But there's one more thing I want you to know about the Nusselt number, kind of related to what we were talking about earlier in terms of, temperature gradients and things like that in the boundary layer, right? And so another interpretation of the Nusselt number is that you can use it to basically assess, or basically to compute the approximate magnitude of the temperature gradient near the surface. And so the higher your Nusselt number is, the higher that temperature gradient is going to be, right? And so what we'll see over the next couple of weeks is that we'll have two ways that we can compute Nusselt number. And so we'll have one formula that's from laminar flow, and then we'll have another formula for Nusselt number with turbulent flow. And what you'll see is that in general, the Nusselt number formula for turbulent flow will be higher, because the temperature gradient in turbulent flow is just higher than that. Okay. All right, and so that's the Nusselt number. Right, and so next we'll have Prandtl number. Okay. And Prandtl number is just a very simple ratio here. And so it's a ratio of nu divided by alpha. Right. Where nu here, this is the kinematic viscosity of the fluid. And alpha, this is something that we saw, very early on in the class. This is the thermal diffusivity. And then even though these things might seem like they're very different ideas, right? So one you have viscosity, next you have very thermal quantity. Actually these two have the exact same units, and so the units for both of these guys are typically meter squared over second. Right? And so because they have the same units here, they cancel out, and we have kind of a proper ratio. Okay. And so this Prandtl number right here is going to be a ratio, between these two things, and I'll tell you how to kind of physically interpret that on the next page. Okay. Any questions on this so far? Okay. All right. So let's talk about what the Prandtl number represents. Okay. But let's start with what each of the different terms in Prandtl number actually represent.
Professor, can you go back really quickly, please?
Yep. Mm-hmm.
Okay, thank you.
Mm-hmm. All right, so let's talk about kinematic viscosity first. Okay. And so kinematic viscosity, probably as you know it, is just another form of viscosity in a fluid, right? But another name that people call it is momentum diffusivity. Right? And the reason it's called that is because the viscosity here tells basically how easily momentum transfers in the fluid. Right? All right. And so I think we had kind of a brief discussion of this last time with the honey jar, right? And so if you take a jar of honey and then you kind of turn it upside down, it takes a while for that honey to come out. And the reason for that is because the walls of the jar themselves are stationary, right? And so you can say that they have zero momentum. And so because honey is a very viscous fluid, what that means is that momentum travels really easily throughout that fluid, right? And so the fact that you have the walls of the jar with zero momentum, that information travels through the fluid, very easily in honey, right? And so that causes, the honey to flow really slowly because basically what's happening is that the fluid next to the walls of the honey jar are basically saying, hey, we're not moving here. We're sticking to the jar, and that information travels really quickly throughout the honey. Right? You compare that to a glass of water, which has relatively low viscosity, right? And you turn that upside down, the fluid next to the walls will stick to that, but then that information doesn't travel that quickly throughout the fluid, right? And so what happens there is that gravity takes over, water spills onto your desk, it gets everywhere, it gets everything wet, you're upset and everything like that, and it's not a good thing. Okay. And so viscosity here, you can think of it as how well momentum travels. Right? And so with that in mind, now that we have alpha here is thermal diffusivity. Right? And so if you remember kind of from early on in the class, thermal diffusivity is kind of a combination of, heat capacity, thermal conductivity, and all that stuff. And this basically expresses how easily, thermal energy travels in the fluid. Right? Okay. Great. And what the Prandtl number here is basically just a ratio of these two quantities. Okay? And so, the upside of this is that, depending on the viscosity and depending on the thermal diffusivity, these are the primary parameters that determine how quickly the boundary layers grow. Because if you remember from last Monday, when we talk about the boundary layer, there's two boundary layers, right? So we have the fluid boundary layer, which is the velocity boundary layer, and we have the thermal one, right? And we talk, and if you remember, from last week, these two things usually don't coincide, and so usually one grows faster than the other one, right? And so what this Prandtl number does, because it's the ratio between viscosity and thermal diffusivity, basically what the Prandtl number basically tells you is, how fast one boundary layer will grow relative to the other one. Okay. Our question. So, what would be an example of momentum diffusivity? So, the example is the is the honey jar, basically what I told you, right? And so another example that you can do, which I don't recommend because it would take a lot of honey, is that you can kind of fill a kind of a container, with the fluid, right? And then this container would have to have kind of a bottom which you kind of pull out, right? Right. And so what you should experience, or what you should see, is where if you try to do this experiment with honey and you kind of pull the bottom out, what's going to happen is that the entire thing of honey is going to start kind of travel towards you, right? That's because the momentum of the bottom layer is going to basically travel up through the fluid, really quickly. But if you do the same experiment with water, right? So you fill a container with water, you kind of pull out the bottom. What's going to happen is that eventually the top of the fluid will start to move, but it might take a little bit of time because the viscosity of water is not that high. All right. Any final questions on this before we end for today? Okay. All right. So there's a little bit more of this that I want to talk about on the Prandtl number, and so we'll wrap that up on Wednesday, and then and then from there we'll launch into the next set of lecture notes, which is external convection. Right? All right. So thank you guys for tuning in today. I should have your midterms graded by Wednesday, and so we'll talk about that then. And so have a great rest of your day, and I'll see you guys on Wednesday. Thanks, guys.
Professor.
Thank you, Professor.
Thanks, guys.
Oh, Professor?
Yep. Mm-hmm.
Would another example for the for that moment diffusivity, would cornstarch plus water be another source, like where it shows like a momentum is hard to travel through that one, or sudden impacts?
That's an interesting one, because a cornstarch and water is what we call like a non-Newtonian fluid. And so with those ones, because normally this viscosity here, or the momentum diffusivity, is a constant. So if you have like water, it's constant all throughout. But with cornstarch and water, the viscosity of that actually changes depending on how you agitate it. And so with cornstarch and water, if you agitate it more, so like if you punch it or something like that, then the viscosity actually goes up pretty rapidly. And so that's why you have that thing where you can ride a bike over a pool of cornstarch and water, but you can also jump into that pool and kind of sink into the bottom.
Okay.
Yeah. So it's kind of a totally different beast in that case.
So would it be kind of like a step function almost, like that in like 308? Where like from a certain point it goes from being you could sort of move through it to where then, or no, never mind.
Kind of. I mean, I mean, the viscosity is going to depend on how much you force it, right? But it's kind of much more of a kind of a regular curve rather than kind of a step function, because there's no critical value to non-Newtonian fluids. It's kind of more of like a gentle thing. Yeah.
Okay. All right. Thank you.
Yep. Mm-hmm. Ahmed, Melody, did you guys have any more questions? Okay, so if there's no more questions, I'm gonna go ahead and close the call. So have a great rest of your day, and I'll see you on Wednesday.